Our next speaker is Juan Manuel González Brantes from the Pontificia Universidad Católica de Chile, and he's going to talk about exploring Rayleigh-Faber-Krahn inequality. So please, Juan Manuel, go ahead. I will let you know when you have 5 minutes remaining in your talk.
Well, okay, thank you so much for the introduction. My presentation shall be about trying to prove Rayleigh-Faber-Krahn inequality within physical assumptions, and it will be divided into two parts. First of all, what is Rayleigh-Faber-Krahn inequality? It is a known result of spectral analysis in maths that establishes an ordered relation between the lowest eigenvalues of the spectra for two different domains. Here in the definition, there is a theorem. Omega in R2 is a smooth bounded and open any domain, and open star omega star is its isometric ball, what is a disk for the n equals to 2 case. Well, here is a remark. The reason of considering n equals to 2 will be clear later. There are a lot of proofs for this result, but most of them are based in maths. In fact, this isoperimetrical inequality was proved for 2 dimensions by Faber in the 23, and dimensions higher than 2 by Krahn in the 25. But, however, it was not until ending the 90s that it was demonstrated using physical assumptions. In his paper, Laszlo used variational principles and elliptic theory to address the dynamics of an electron subject to a uniform and constant magnetic field. Here I graph the magnetic field in the two regions and two domains within the omega region mentioned before. Here is the omega region mentioned before, and here is the omega star region. This theoretical frame could be a little unfamiliar to a physicist who does not know functional analysis, and that is why I propose another approach that divides this problem into two parts. One, to find the lowest eigenvalue for the omega region, here, and other, to find the lowest eigenvalue for the omega star region. So here in the picture, omega and omega star domains are here, its boundaries, and the magnetic field are represented in this diagram. And for completion, the paper of Laszlo it's at the end in the main references. For the first part for this work, which is trying to compute the lowest eigenvalue for the omega region, we address using a Hamiltonian approach, whose effort seeks to determine which is the best Hamiltonian to pose the Helmholtz problem. Using polar coordinates r and theta, the radial and the angular position respectively, and incorporating minimal coupling to include the effects of the magnetic field and the electron dynamics, we postulate the following magnetic Hamiltonian given by Juan, where the parameters are described under. For example, delta is nabla squared, the polar coordinate Laplacian, h bar is the Planck reduced constant, and so on. Notice in natural units, we have two. This part of the equation 1 is the natural units, which allows us to set the associate Helmholtz problem given by 2 now, to get the spectrum. And here is the eigenfunction. We admit a separable variable function, and lambda is the eigenvalue for 2. Inserting 2 into 3, we get the following PDE. Coupled with radian f and angular g eigenfunctions, as I show here. But however, this Hamiltonian and the orbital angular momentum diagonalize in the same discrete base of eigenstates m, allowing to solve the angular problem independently as shown by 4. So using 4 into 3, we obtain an ODE, an ordinary differential equation, for the radial eigenfunction, which is singular at the origin, as I show here in this term and in this term, and cannot be solved through analytical techniques. Well, one way to approach this problem in the ordinary differential equation is to consider a numerical analysis based on Frobenius arguments, that is, taking a trial function very close to the origin and expanding it in small orders to repair the singularity near the vicinity. Notice how the coefficients of this function behave, as I show here. If we choose the shooting method, we need to propose three conditions to determine completely the problem: normalization at the origin, null derivative, and Dirichlet boundary. C2 and C4 are coefficients from these trial functions, and I only get with C2 because C4 only gets more precision to the analysis. Well, here is the numerical radial eigenfunction made in Wolfram Mathematical. From this moment on, the notion of radial eigenfunction, will be the last figure. Now we can calculate the lowest eigenvalue for omega once we already know now the radial eigenfunction and impose the mentioned condition. Since m is in the integers, as I show here, but we need linear independence, we consider only natural ones plus 0. Thus, immediately we know that in m equals to 0, we have the lowest eigenvalue and it works approximately 6. This is the magnetic number, so I think it's obviously I think that is m equals to 0 gives the minimum of the spectrum. Our focus is to find now the lowest eigenvalue for the disk, that is the omega star region. For this purpose, we consider the integral in R2 posed by Van Guria for Nestot, Meyer, and Van den Bosch in the paper of Van den Bosch for 2017, given by 6. This is the R2 integral, which is definitely positive because there is a bilinear form. If we subsequently integrate by parts 6, we obtain 7, where one can note that it has been defined a calligraphic f function which inherits the definite positive condition. This function, calligraphic f, will provide us with an inequality whose lambda could be bounded. I mean, this function inherits this condition, so we can pose some conditions into this eigenvalue to bound it. Since we are interested in the lowest eigenvalue, we can take advantage of the inequality obtained in 7 held at equality. This allows us to deduct 8, and then replacing into the calligraphic f definition, we get 9, providing a relation between lambda and known quantities. Here, the strategy will insert the disk in another region similar to omega and try to bound both upper and lower, which allows bound the lowest eigenvalue for the disk and then prove Rayleigh-Faber-Krahn as the following image tries to explain. Well, here the circular region is the maximal domain what we could inscribe in omega. So this is the disk, and rho is the in radius for the omega star region. We said that alpha is a complex number, so we can study its behavior to infinity, but results in this lower bound for the lowest eigenvalue. This quotient recalls a known result in variational calculus, the Barta-Duffin's principle. As I mentioned here, is the Barta-Duffin's principle state at the 37 and 47 years for the last century, and it says this. Note we have a kind of symmetry in the definition or in the structure. Due to the symmetry involved in the Barta-Duffin principle, Now the work is to think some good functions bound to the lowest eigenvalue to get its numerical value. For example, we expect to try for psi with the Bessel function for the disk. But as I show here, although they are good functions, well, the first set of Bessel functions at first order is equals to 2.44048, but they are really so far to be a good bound as Banuelos and O'Carroll showed 27 years ago. Is the bound. So it's a good bound, but quite impressive. As a final conclusions, well, we addressed the Rayleigh-Faber-Krahn problem following another approach based on Erdős idea. I mean, Erdős attacked the problem using elliptical theory and variational principiums, so it would be so far from the knowledge of the physicist of a physicist in maths. So I try to give the another approach based on find the lowest eigenvalue for the disk and find the lowest eigenvalue for the omega region on any omega region. For omega, we get the lowest eigenvalue through the use of a Hamiltonian Helmholtz equation and computation implementation due to the singularity who appears in the radial terms in the inverse powers. For omega star, it has been obtained a lower bound for the lowest eigenvalue once we take advantage of the Barthes-Duffin's principle, but there is an incomplete work because, however, is an upper bound needed to compute Rayleigh-Faber-Krahn. I mean, with this result, we can only bound for this part of the region, but now we have to find a good function in order to describe this region and try to bound here and over here, and this bound and find a bound who would be more precisely than what I found. I wish to thank my Professor Rafael Benguria, who worked with me along with this trouble. Here is the main references. Well, the first is the Lazo-Ledoche. The second one is where I take the advantage for the density integral. Barth and Duffin papers where they describe their Barth-Duffin's principle, and the Banuelos and Carroll of 1994 of the good bound for the disk. Thank you so much for listening.
So thank you very much, Juan Manuel. Thank you for the talk. We have time for questions. I don't know if there is any question. Danilo, please go ahead. Danilo?
Yeah, is there any requirement on the shape of the surface? I mean, convexity or something like that, or is it allowed to?
Of the omega region, you said?
Yes.
Well, that is a very interesting fact because in order to trying to prove the upper bound for the lowest eigenvalue for the disk, I think we should try with some regular shapes for the omega region in order, for example, try to use perturbation theory, and in this point perturbate a more regular region, and we could know how it will be behaved at this perturbation. So it's a very interesting question. How does shape the omega region, but in general, it has no importance for it has no relevance for the study of this approach.
Okay, thanks.
Yes. I don't know if there are any more questions. Maybe I have one. What about different manifolds, Juan Manuel? I mean, if you go beyond, I mean, explore different manifolds.
Yeah, different manifolds. There is an actual work made by Nadirashvili, who I think it's 27, the 2017, sorry, who talks about the different manifolds. I have to admit that I'm not very close to the language of manifolds and so on, but it's very interesting who Nadirashvili plays with the different manifolds and tries to get bounds for the lowest eigenvalue not only in Rayleigh-Faber-Krahn in other isoperimetrical inequalities, but in certain, for example, concepts of um, differential geometry. So I think that is a good one for starting to study the problem in other approach.